Rad Niazadeh cipher. He's going to tell us about fast forward pricing for original advertising auctions.
Thanks everyone for coming to my talk, and I want to thank the organizers for having EC this year in Ithaca. It feels really great to be back home after a while. So today I'm going to talk about fast core pricing for rich advertising auctions, which is a joint work with my collaborators, Jason, Nicole, Reza, and Brandon. I think all of them are in the audience. So let me get started by jumping straight to the problem I'm focusing on today, which is a sponsored search auction. Sponsored search auctions are at the core of the business model of the search engines, and we all know that they are the way that search engines make money, although there are people outside of this audience that probably they have no clue about this. So I don't want to waste any more time from the audience, but let me just remind you of a classic standard model in this industry, the separable CTR model, which is essentially looking at the ad auction as selling positions. There are positions ranked based on their clickability, and then there are single-dimensional bidders that they have value for clicks, and the question is which bidder should go to which position. And then there is this celebrated standard solution, generally second price auction, or GSP, that has been run by the big players of the game in this industry, Google AdWords and Bing, and also Yahoo. And it has made billions of dollars of money in this industry. If you just look at Google for the last 17 years, only in like 2017, it made like $95 billion out of GSP. So it shows that GSP works very well in practice. And thanks to these folks who actually won the Test of Time Award this year at EC, we understand this equilibrium behavior pretty well, even though it is non-truthful. We have a lot of handle over GSP, so it is a very well-celebrated auction in practice. However, when you think about it, it is very restricted to this position environment. In fact, if you go beyond position, it's not even clear how to define GSP. So in particular, in like modern ad auction platforms, we are dealing with a situation that ads have multiple probably like figures, like shapes, sizes. For example, there might be two advertisement versions. So one of them is an 8-liner with links to the website. The other one is like a short 3-liner. And the question of like assigning the lines of the platform to the advertisement is essentially like a combinatorial auction. So when you think about CAA, the first thing that comes to mind is running VCG auction, Vicary Clark's Grove. And that's actually a possible solution, but I'm going to talk about it later. So let me show you a demo of what do I mean by combinatorial ad auctions. I think one of my co-authors in particular is going to like it a lot. So I don't know if I can play it now. Man. OK. Good. So I don't know if you use Bing, but this is Bing search engine. And I don't know why my video is stopping. So it was supposed to show that I'm searching something on Bing. OK, so I'm going to stay here. So, OK, I'm going to type flowers. And as you will see, the advertisements are going to pop up. So there is a section for advertisement. It has some number of fixed lines. And you know, different versions of these different advertisements, they have different decorations. Basically, some fixed number of lines, and you can pick each like one of the decorations for each advertisement. And the question is basically how to pack these guys into the advertisement section of the browser. And this is more or less like a knapsack problem. So one thing I want to point out is, you know, that if you think of lines as goods, then goods here have complements. So in contrary to the separable model, we are not in a fully substitute environment. So now if you think about VCG, VCG is great. It is efficient. It is truthful. It is computationally tractable as long as you have access to an oracle for computing the maximum welfare allocation. And honestly, it's not a terrible idea to use VCG. Yahoo has been using VCG, at least when I was interning there. But still, you don't see it to be that common in practice. And if you want to know why, I would say you should ask this question from people who try to put auction theory into work in another application domain, in particular, Larry and Paul Migrom. Many of these guys that I'm talking in this slide are actually in this room, so it feels great to give this talk in front of them. So Larry and Paul, they have this awesome paper called Lovely But Lonely Vicary Auction. And they argue that VCG is a powerful auction when you have substitutes, but when you have complements, there will be a list of undesirable properties of VCG from the standpoint of a practitioner. In particular, it has low revenue. Bidders might have the incentive to use fake names and disaggregate in the auction. It's called shield bidding. And there might be groups of people that they want to have a blocking coalition or form a collusion, and etc. So for the multi-billion-dollar industry that these folks were designing auction for, in particular FCC Spectrum auction, which helped the US Treasury in 2017 to decrease the deficit by $7 billion, the idea that these guys and many other people who thought about this for different spectrum auctions across the globe was minimally sacrificing the incentives in order to get rid of the list that I just mentioned. That was one of the goals. And I would say one of the early solutions was the ascending proxy auction. We heard about it in this session. And then later on, it has been generalized to a family of auctions, core-selecting package auctions. And this is going to be the type of solution that I'm going to talk about and how to adopt it for the sale of ad space. So we heard about core, and Ben, thanks to Ben, so we know a definition for core. But let me informally define a core for a second time for you. For the sake of this slide, imagine that bids are going to be treated as the true valuations. Like imagine that the bidders are bidding truthfully. Now, I'm asking you this question. So what would be a set of prices so that if you charge those prices, then the bidders won't have any incentive to form a blocking coalition with the seller? Meaning that, so if you imagine you focus on a particular subset of the bidders, then you need the total utility that they get from the auction plus the utility of the seller to be at least the maximum welfare that they would have get by forming a blocking coalition. And I just defined it for the reported, for the values, but you can actually define this concept for reported values. And then this linear inequalities will give you a polytope. So it's called core polytope. The coordinates are the utilities of the winning bidders. And this polytope has a lot of nice structures. In particular, it is inside a hypercube whose corner is the VCG point. And 0 is always in the core, which is corresponding to first price auction. And let me define another set of core points. So this is called the bidder Pareto optimal frontier of the core, which are the set of all the core points that are not Pareto dominated by any other point in the core. And these are of particular interest. In particular, there is this core point called quadratic payment rule, the closest point to VCG in terms of norm 2 that has been massively used in the spectrum auction. And there are other choices. In this talk, I'm going to focus on the bidder optimal core point, and you will see why. So there are pros and cons when you switch to these category of auctions. At least if you treat the bids as true values, then we will have more revenue than VCG. It's even clear from this slide. There will be no shield bidding. And by definition, it is group strategy proof. And then the bad news is this is not truthful, so we are going to sacrifice something. And also now we have to find an answer to this question, that which core point are we going to pick? And if we want to pick that particular core point, how to compute it exactly? So when you think about adapting the core auctions to the sale of ad space, these two are going to be the questions that you have to figure out an answer for. So here are the challenges, computation and incentive. Let me address the second one first. So similar to the spectrum auction, I'm going to pick a bidder optimal core point. And actually, there is a reason that this type of core auctions can be applicable in the particular setting of ads. The rough idea is, if you assume that the bidders are learning their bids or essentially running some natural dynamics, if you pick a bidder optimal core point, it can be shown that it can coordinate the bidders in order to reach the full information Nash equilibrium of this game. So let me make this a little bit more concrete. Imagine comparing two auctions, first price auction and a bidder optimal core auction. Both of them are in the core. Suppose I'm running 2 rounds of these 2 auctions, and in the first round, in both of the auctions, bidders are bidding truthfully. So if you think about the first price auction, the reported utility of the bidders is going to be 0. So essentially, bidders don't get any information from the auctioneer. So it's not clear what do they do in the second round. But if you think about the bidder optimal core auction, then actually there is a way for bidders to land into a full information Nash equilibrium of this game, thanks to a nice theorem by Bob Day and Paul Nigrom, which is saying that if you bid truthfully in a core auction, then if the core auction was a bidder optimal core auction, then the prices would be what you should have bid at the first place. So that means that this 2-step dynamic can actually land into the full information Nash if players coordinate. This is not happening in reality, but informally speaking, you can imagine that if bidders are running some natural dynamics and they're targeting for the equilibrium utility, then you expect that at the end they're going to land in this full information Nash equilibrium, and therefore the utility that they get is going to be what they would have get in a truth-telling status. So I'm swiping a lot of details under the rug, but I just want to point out that incentive is not the main issue here, and actually the main issue is computation. And that's simply because of the fact that we probably had around 87 spectrum auctions in the US since 1994, but in a month, Bing is running 9.6 billion auctions. So there is a huge gap between the required speed in these 2 application domains. And so let's address this computational question. What is a benchmark? We try to compete with VCG. So VCG has access to an oracle that can find the maximum welfare allocation. And in order to compute the allocation and payments is making number of bidders plus 1 calls to the allocation oracle. That's really my benchmark, and I hope I can achieve this amount of computational tractability. So in this literature, there is a huge line of research on awesome algorithms that has been implemented in practice. I call them core constraint generation family. And these algorithms are essentially semi-fast heuristics. They don't have theoretical guarantees. However, they work very well in practice. For the purpose of the spectrum auction, they have the desired performance and the speed. But this is not fast enough for adoption. So if you use them, you won't be able to run things that are happening 9.6 billion times in a month. Another solution is always using LP solvers, and that unfortunately is not fast enough, even though it has theoretical guarantees. So we show there exists a deterministic combinatorial algorithm that can actually find almost bidder optimal core point with only quasi-linear number of calls to the allocation oracle. And I have to say that this is not exactly the allocation oracle. It is a modified version of the allocation oracle that is very common in this literature called truncated welfare maximizer. So I'm going to give you more details about this algorithm, but before that, let me show you what we did on Bing. So we ran simulations on big data, and the results were surprising. So we actually could get around 98 more revenue than VCG, which is crazy. And if you compare with the simple GSP without any optimized reserve prices, we could get 19% more revenue. We couldn't compete with the GSP with the optimized prices, but that's a separate issue because reserve prices, when you optimize and using machine learning algorithms, then it boosts the revenue, and you can use reserve prices for any auction, even if you are running core. And in terms of running time, we definitely were slower than VCG, but we were in the same order as VCG and faster than the heuristics that I mentioned in the previous slide, and definitely LP solvers. So in the remaining of the talk, I tried to briefly give you some technical details about how does the algorithm work. And I need to make things a little bit more concrete. Let me define some notations. So we are talking about combinatorial auctions. Let's say N is the set of buyers, and we have one particular player in this game, which is seller. I denote seller as player 0. Let's say VIs are the true valuations of the players, and BIs are the reported values. The auction picks an allocation, which is the partitioning of the items, and payments that will be charged to the bidders. Items go to the buyers, and money goes to the seller. Let's say pi 0 is the total collected revenue by the seller, and pi I is the reported utility of bidder I. I'm going to use this welfare function with respect to reported values all over. So with these definitions, you can actually define the polytope of core utilities. It is what I used before. For every subset of bidders S, the summation of their reported utilities should be at least the welfare minus the revenue. And then I say an auction is core selecting if for any reported values, it picks an allocation and payment, so that the allocation is maximum welfare allocation with respect to the reported values. And the prices are such that the vector of utilities is in the core with respect to the reported values. So here is my water filling algorithm. So the high-level idea is, we have this polytope, and first price auction is in the core, basically all 0 points. So we want to greedily approach the Pareto frontier of the core while we are staying in the polytope. That's essentially the idea. So to see how to do that, let's rewrite the core. Believe me, this is another way of rewriting the set of linear inequalities that I had in the previous slide. So if you just stare at this for a second, then you realize the right-hand side is the only part that depends on set S. So then here is an interesting observation. So that's also decomposable across players. Let me tell you another observation which is interesting. So imagine that for a second, for one particular subset S, the core constraint is tight. Now that means that if you want to increase the utilities pi I, then you cannot increase the utility of anyone who is not in set S, because if you do that, then you will definitely go outside of the core. Another key observation is, okay, suppose you start increasing the utilities of a subset of the bidders S, then that decreases the slack of any constraint that is corresponding to some set T, as long as T is not a subset of S. Because if T is a subset of F, you're going to decrease or increase both sides equally. Okay, so here is going to be what you need to do. Imagine we have like 4 buyers. These boxes show you how much slack you have for every constraint. And remember, we have one constraint for every subset of the bidders, basically exponentially many constraints. So you start increasing the utilities until you hit one tight core constraint, in this case, the purple one and the orange one. So because the orange one is tight, you have to kick out a person who is not among the orange ones. And because purple is tight, you have to kick out the person who is not in the orange. And among the remaining bidders, you start increasing the utilities again until you hit the next tight core constraint. You repeat the same process again and again until you are running out of the bidders. And this is the moment that you have to stop. And it's not that hard to show this is going to be a bidder Pareto optimal core point, because essentially you cannot increase any of the utilities anymore. And if you do that, you're going to go outside of the core. However, the issue is, actually, I have to show you how to do 2 tasks in order to make this algorithm implementable. So the first one is how you can find a feasible subset of bidders to move toward the Pareto frontier and still stay in the core. That's the first thing that you have to figure out how to do. And the second is I have to show you how you can jump from one tight constraint to another in a fast fashion. So it turns out that the answer to both of these computational questions will be reduced to sending order log n number of queries at every iteration of the previous algorithm to the truncated welfare maximizer. You can think of these as basically a black box that you input the bits for every bundle and a vector of utilities. This black box decreases the bit for every bundle by the utility and finds the maximum welfare allocation. It has been all over the place in the core literature, and there is a reduction that shows, both of these challenges can be done by log n number of iterations, by log n number of calls to this oracle. So I'm not going to provide any more details. I hope these fancy pictures can convince you to check the paper for more details. So let me wrap up. So I talked about core selecting auctions and how you can use them for sale of address space. I briefly mentioned the water filling algorithm, which is a simple quasi-linear time algorithm that can find some particular bidder optimal core point. I have to mention that we don't find a quadratic payments rule or a minimum revenue core point. It's just some point on the Pareto frontier. So it would be interesting to understand which bidder optimal core point actually we pick. We run, probably I should say, simulations on Bing, which showed a boost in the revenue with respect to VCG and simple GSP. And honestly, there are many interesting open questions left. So one of them is analyzing natural dynamics. We could analyze it for very simple settings, but for complicated settings, we were not able to do that. Computing revenue monotone allocations in a fast fashion, that's pretty interesting. Also, another interesting question is actually finding the minimum revenue core point that Ben talked about. I don't know how to do that. I just find some Pareto optimal core point. There is a path parameterization for our algorithms. So at some point, I showed you that we can uniformly increase the utilities, but probably you want to follow another path. And one question is, can you parameterize this path in order to end up with another bidder optimal core point, probably with more desirable properties? I don't know the answer. So with that, I'm going to conclude my talk, and thanks for your attention.
Questions?
Can you talk to people at Microsoft about actually implementing this?
Probably Nicole has an answer. So we already started that kind of like a series of meetings. So yeah, so I think they are considering it. But I'm not sure how much I can tell more about it.
So given our work and Ben's talk about how different core selector rules can
Yeah.
have very different incentive properties,
True.
I would be concerned about just picking any random point on. So do you have any ideas how one could extend this work towards finding specific?
I think about that as actually a future research direction. So there is a distinction between what I talked about and what Ben talked about. So I think the first distinction is the difference between a full information Nash equilibrium and a BNE. So if you pick a random bidder optimal core point, then you can say some things about the incentives of the auction if you think about this full information Nash equilibrium, but there are a lot of critics about the full information Nash. I mean, I don't want to spend any more time on that, but so it's not a very acceptable solution to many economists. But then in the setting of adoption, because of these natural dynamics, we believe it is still acceptable, but I totally agree with you. So it is a very natural question to ask, like, how can we find another probably bidder optimal core point that matches the setting that we are designing auctions for? So yeah, that's an interesting question.
Yeah, that's security.
Thanks. Thank you.